All right, so the first part of section 1.3, I think you should be able to figure out pretty much yourself. We're introducing the idea of a vector, and real briefly, when we talk about vectors, we're there's a couple things that in linear algebra terms, we're talking about a column matrix, so it's a 2 by 1 matrix, not a row matrix, so not a 1 by 2, but it's got to be vertical, like you see there, and that's what we know as a vector, and what you'll need to get used to that terminology. And of course, with vectors, we put this little arrow above it. But in the textbook, it's all bold and things like that. But we can't write that down. Now, vectors have a graphical interpretation as well. Real briefly, a vector is just can be represented by an arrow of a certain length and going in a certain direction. So we have certain quantities that are vector quantities. In other words, we need to know both their direction and their magnitude. For instance, force. When we talk about force, it's not good enough to just know how much force. We need to know what direction the force is coming from. So graphically, we can represent that vector by, of course, the arrow. The arrow shows the direction of the quantity of the force, and the length of that shows the magnitude, and that's a vector. And so we can have all kinds of vectors going in all kinds of different directions with all kinds of different lengths. But what we typically do is we'll talk about a vector being in standard position, and what that means is it starts at the origin and it goes. Let's try that again. It goes out from the origin. And where does it end? Well, there's going to be a correspondence between the point it ends, 2, 3, and the components of the vector. So we can talk about the vector 2, 3 as given right here, and we can think of it graphically as this right here. And so you'll get to see that in the first part of this section, and hopefully it'll all make sense. You can add vectors, and they're very easy to add numerically. Graphically, you're basically putting them end to end and then drawing a new vector to show where they end up. So, if I graphically add vectors, here could be my first one. My second one might be, something like this, and so I could write it, just from that end of this vector, and then my result would be this. This would be the answer, the resultant vector. So you can add those. They're pretty simple to deal with. But we don't deal a whole lot with these things graphically. This vector we're talking about is in R2. So we'll write it like that. That means two-dimensional space as represented by a regular plane xy axis. If we have a 3 by 1 vector, okay, if we have a vector like this, 3 by 1, that is a vector in R3, three-dimensional space. You have an x component, a y component, and a z component. Okay, so, and then of course we can have our vectors be longer. They can be in R4 and R5 and R6 and so on. But what we're interested in is this idea of linear combination of vectors. And that's a pretty simple idea. A linear combination of vectors can be expressed like this. It's going to be some constant times your first vector plus, let's use a better notation here. Okay. So it's going to be some constant. I'm going to back all the way there. All right. So linear combination is going to be some constant times your first vector, v sub 1, right? And I'll put the arrow there, but I guarantee you that at some point I will forget to do that. Plus a constant times a second vector plus some constant times your third vector. However many vectors you're finding a linear combination of. So you're adding those three vectors with multipliers in front of them. And that is a linear combination. Very easy to calculate, very easy to figure out what they represent. It's interesting when you take a couple vectors in, say, R2, and start doing linear combinations of them. I'm just going to point you, I'm not going to try to draw it here, I'm just going to point you to page 28 in your book, where they're taking a linear combination of, they're graphically displaying the linear combinations of the vector -1, 1, and the vector 2, 1. And what you kind of do is you get this grid that looks like it's no longer a square grid. The square grid, the regular XY grid that we're used to, basically, you know, if I were to put in all our little, if this were graph paper, right? Let's make our axes a different color. So there's our axes, right? So the points that you have on our regular, very familiar XY, those represent points that are linear combinations of the vectors 1, 0 and 0, 1. And so we get this nice square square grid that we're used to. And so when we talk about, say, a point, say the point, 2, 5, that's actually, graphically, in terms of vectors, it's 2 of the V1 vectors plus 5 of the V2 vectors, and that gets you to the point 2, 5. Okay, that's a little bit of abusive notation, so I don't want to use the equal sign there, but that's what would happen. So when you take linear combinations of these two vectors, 1, 0, and 0, 1, you get a grid and you get points on that rectangular grid. But what you see on page 28 is, what if you don't use those two vectors, v1 and v2, as your kind of your basis, but instead you use something like the two that are given here? Well, you still get a grid, but now it looks like a hexagonal grid. You could still locate points on that grid, but now they would be in terms of v1 and v2, this v1 and v2, I should say, instead of this v1 and v2. Okay, so a location on the, for instance, a location on some point here, I don't know, we'll just, might require, that point might require us to take, I don't know, we'll just say 2 v sub 1s. Well, let's see, let's do it this way. Yeah, we'll just go let me say 1 v sub 1 and 2 v sub 2s, and you get this point that we're talking about. Okay, so in other words, here's what v sub 1 looks like, or I'm sorry, negative, yeah, that's v sub 1. V sub 2 looks like this. And so if you take a v sub 1 plus 2 v sub 2s, you're probably more up in this range, right? Up in here. Let me find the right button here. Interesting. You're probably more up here. Let's not try to erase it. Probably more up here. So this point would be expressed as 1, 2 in the notation of this new basis. Anyway, we don't play a lot with that, but that diagram, that picture on page, or that figure on page 28 shows you that. So we talk about linear combinations, and what we're really interested in doing is seeing if we can create other vectors using linear. So can I build other vectors using these two vectors? So let's look at an example of that. So the question would look something like this: can 2, 4 be written as a linear combination of, we'll call them U to make it easier, U, which is that vector, and V, which is this vector. So what we're asking there is this: is it possible for me to take some constant times U plus some other constant times V and get 2, 4? Okay, so I'm using U and V, a certain number of U's and a certain number of V's, to end up with 2, 4. That's what it means to be a linear combination. And so if I actually put, so we'll take this little equation, when we fill it in, will look like this. We throw the U in there. We throw V in there. And we ask, is it possible for us to find those constants so that that is that is a true equation. I shouldn't have put this little V in there because I actually put the vector in itself. Now, just watch as this goes through, because what's going to happen here, when you multiply a scalar times a vector, you get this. So 1a sub 1, 2a sub 1, plus negative 3a sub 2, 2a sub 2, and that needs to equal 2, 4. And then we've got an addition, and the way we add vectors is we just add like components. So 1a sub 1 gets, in this case, subtracted, or subtract 3a sub 2, and on the bottom we have 2a sub 1 plus 2a sub 2, and we want to know, does that equal 2, 4? And that leads us simply to this system of equations: a sub 1 minus 3a sub 2 equals 2, and 2a sub 1 plus 2a sub 2 equals 4. And so if we can solve that system of equations, then the answer to the question is yes, and we're able to, we've shown that we can write these equations as, or this vector as a linear combination of the other two vectors. Okay, in other words, we've kind of built, we can build 2, 4 using a certain number of U's and a certain number of V's. Okay, so let's just throw that in our calculator real quick and solve it, because I know you can do that by hand, so let's just let the technology do it. And so with just a real quick turnaround here, we see that the solution, and we could have seen this probably from the get-go, but the solution is going to be this: a sub 1 equals 2, a sub 2 equals 0. And that particular linear combination gives us the answer to our question, shows us that yes, we can write our vector as a linear combination. The answer would be 2 a sub 1's plus 0 a sub 2's. That does equal 2, 4. So we've built 2, 4 out of a sub 1 and a sub 2, or we've written 2, 4 as a linear combination of those two vectors. Okay. Now, we introduce another term here, and it's called a span. So let me write it down. We would talk about the span of a couple vectors. In this case, let's just continue talking about the two that we're talking about here. So the span of uv represents all of the vectors that are linear combinations of u and v. Or another way to think about it is all of the vectors that can be written or built from u and v. So 2, 4 is in the span. The span is a set of vectors. So 2, 4 is in the span. So we're kind of interested in what the span of these vectors turns out to be. And it turns out that we can build any other vector, two-dimensional vector in R2 out of these two vectors. We'll explore how we know that later. But that's not always going to be the case. So the span of a couple vectors is all of the linear combinations that can be made from those vectors. It's that set. So that's 1.3. That should get you started. And hopefully, if you have questions, you can contact me or bring them up in class.